Hey, okay, so we're going to discuss thermal equilibrium, heat transfer, and thermal equilibrium. Darn it. All right, let me share. Okay, come on, pop up. Heat transfer and thermal equilibrium. Very common sense topics, right? If that phrase even makes sense, right? So come on, iPad. Come on, there we go. Okay, let's see. When we discuss heat transfer, think why are we even discussing heat transfer? What you want to realize is that heat always transfers from hot objects, which obviously have, thus the higher temp, right? Which is a measure of the average kinetic energy, okay? And it always transfers from hot objects to cold objects, right? And because those objects are cold, they are at lower temps, which means, a lower average, average kinetic energy, right? And we know that the heat lost is equal to the heat gained. And we'll make this negative because the negative is negative, right? The heat lost is negative. So it's always equal to the heat gained. So that means negative Q lost equals Q gained, right? So recall that temp, right, temperature is a measure of average kinetic energy. So same temp equals same average kinetic energy. So what does that mean? That means that in a sample, say of a gas, right, you might have some small particles moving rather quickly in straight lines, right? Until they collide. You might have smaller particles not moving as quickly. You may have smaller particles moving even less quickly or moving quickly, right? Maybe we have some larger particles that are moving at this speed, maybe this speed, maybe this speed, so we have many speeds represented. Right? If we have more greater speeds present, then we would have a higher average kinetic energy and a higher temperature, right? But this shows us all of the particles moving at different speeds. Remember that average kinetic energy, let me write this over here. This is important. Remember that kinetic energy is equal to 1/2 mv squared. This is the mass, and this is the velocity, right? And we've discussed this. As mass goes up, the velocity goes down. Right? But the kinetic energy at a given temp is constant. Let's make that average. Right? But the mass and velocity are indirectly related to give the same average kinetic energy at a different temp. Okay. I don't know. We've talked about heat is transferred from hot to cold. The amount of heat lost is equal to the amount of heat gained. All right, that heat is typically measured in joules, right? Joules, a measure of heat. And right, first law of thermodynamics is energy is neither lost or gained, but is transferred, okay? And we've already talked about it's transferred from hot to cold on a particular level. The kinetic energy of the substance with the higher, at the higher temp is transferred to the particles of the substance at the lower temp, right? So the molecules collide, the molecule with the larger average kinetic energy moving faster transfers some of its energy to the particle that has the lower kinetic energy, and this continues to the particles of the substance with the lower kinetic energy, right? And this continues until what? Until what? Until thermal equilibrium is reached. Okay, right? At thermal equilibrium, what? We are at the same temp. So we have the same average kinetic energy. All right, that's basically it, guys. Okay, sorry if I got a little boring there, but I'm gonna go ahead and end it there. All right, stop, share. See you soon.